So I have assumed that lambda belonging to R is an eigenvalue of t. We have to prove this. Lambda I minus t is not injective. It is clear that lambda I minus t is a linear transformation. As I have told you, whenever you are having linear transformations, the linear combination is a linear transformation. So directly I will say, as this lambda is an eigenvalue of t, note that we have to show this. Okay, so as lambda is an eigenvalue of t, so there will exist v not equal to 0 belonging to v satisfying this property t of v is equal to lambda v, as I told you, and by doing some algebraic calculations we will get this. Yes, so some steps are skipped over here, but that is understood. So directly this step is written, and therefore this v will belong where? To kernel of lambda I minus t, but this v is non-zero as it is an eigenvector. Therefore this kernel of lambda I minus t is not equal to singleton 0, and therefore lambda I minus t is not injective. Now we have to prove 2 implies 3. So just let us see what is 2. In 2 we have to assume that lambda I minus t is not injective, where I is the identity map, and we have to prove that lambda is an eigenvalue of A, where A is a matrix associated with T with respect to any basis of V. So this is the important thing to note. We have to prove that lambda is the eigenvalue of A, where what is matrix A? It is a matrix associated with T with respect to any basis B of V, any basis of V actually. So the thing is, whenever you are having a linear transformation, I have already told you, you can always find the matrix representation of T, provided you should have a basis actually. So the same thing is over here. This A is nothing but what? It is a matrix representation of T, but no, with respect to any basis of V. Okay, not only a certain fixed basis, but with respect to any basis. Okay, that is important. So I will assume that this lambda I minus t is not injective. We are going to follow the same path of the previous part. Since it is not injective, I can say that kernel of this lambda I minus t will not be equal to singleton 0, since the result was if and only obviously, and this will imply that there will exist some x not equal to 0 belonging to what? Kernel of lambda I minus t, and this will imply that lambda I minus t outside the bracket x is equal to 0, and this will imply that lambda I x minus tx is equal to 0, and this will imply that tx is equal to lambda x. Is that okay? Because I is the identity map, so ix is going to be x again, and since this is happening where T is a linear transformation, this is also going to hold for the matrix representation of T, and I am going to use this notation for that. So it implies that this is nothing but what actually? This is the matrix representation of T with respect to any basis of V. So this matrix is also going to satisfy this one. Is that okay? Simply T is replaced by what? This, the matrix representation of T. Since the linear transformation is satisfying this, so the matrix representation of T with respect to any basis is also going to satisfy that. Okay, and I am going to call this as A, and therefore we will get Ax is equal to lambda x, and this will imply that this lambda is an eigenvalue of A, where this A is a matrix associated with T with respect to any basis of V. So let us go through the proof. Here you can see, suppose this is not injective, we have to prove this. So this kernel will be non-zero, so we will have some non-zero vector in kernel, it will imply this. It is by the definition of the kernel, we will have this, then we will have this T of x is equal to lambda x, and therefore for any basis this is going to satisfy, and I am going to call it as A, and this will happen. Now since x is non-zero, so therefore lambda will be an eigenvalue of A, and where A is a matrix associated with T with respect to any basis of V. Now we are going to go for 3 implies 4, where we are going to assume this, that lambda is an eigenvalue of A, where A is a matrix associated with T with respect to any basis of V, and we will prove that lambda is a root of characteristic polynomial of A, and this is very interesting to prove. Yes, so I have supposed that lambda is an eigenvalue of A, where A is a matrix with respect to matrix associated with T with respect to any basis. So we have to prove that lambda is the root of characteristic polynomial of A. So as lambda is an eigenvalue of A, therefore what will happen? So as lambda is an eigenvalue, so therefore this there will exist some x non-zero belonging to R raised to n. This is by definition only, such that your Ax will be equal to lambda x. So what it will imply? So this will give us Ax is equal to lambda I x, where I is the identity matrix, right? Just I have introduced that I. This will imply Ax minus lambda I x will be equal to 0. This will imply A minus lambda I outside the bracket x is equal to 0, and x is non-zero. Just note this. So if you observe it properly, this is nothing but a system. Actually it is a homogeneous system. If you recall, Ax is equal to 0 is nothing but what? A homogeneous system where A is a matrix of coefficients and x is a matrix of unknowns. So same thing we are getting here. So this is a homogeneous system of linear equations with a non-zero solution. Since x is non-zero, x is nothing but the eigenvector of A, and that eigenvector is satisfying this system, means this system is having a non-zero solution. So since this system is having a non-zero solution, what can you say about the determinant of the coefficient matrix? We have already seen this before. If the determinant of the coefficient matrix is non-zero, then the system will have a trivial solution, that is a zero solution. But that is not the case. Since this system is having a non-zero solution, so determinant of this coefficient matrix should be what? 0 only. So this will imply that determinant of this A minus lambda I should be equal to 0. And what does it imply? This implies that lambda is a root of characteristic polynomial of A, and that is what we wanted to prove. Let us go through the proof. So you can see this will happen. So this will happen. Yeah. So yeah, have the non-trivial solution. Therefore this will happen. Non-zero and non-trivial is one and the same. Okay. Since it has a non-zero solution, any linear combination of that is going to be a solution. Okay. So therefore has a non-trivial solution, and therefore this determinant is 0, and therefore lambda is the root of characteristic polynomial of A. Now we are going to go for the next part. So now I am going to assume that lambda is a root of characteristic polynomial of A, and we are going to prove that the system of linear equations lambda I minus A outside the bracket x is equal to 0 has a non-zero solution. Now we will assume that the system of homogeneous linear equation lambda I minus A x is equal to 0 has a non-zero solution, and we are going to prove that lambda is the eigenvalue of T. Now since this system has a non-zero solution, what does it mean? It means that we will be able to find some non-zero vector belonging to R raised to n, such that that vector is going to satisfy this system, right? This will imply that lambda Ix minus Ax will be equal to 0. This will imply that lambda of Ix minus, now what is A? Remember, A is nothing but what? It is the matrix obtained by what? Somewhat like this, right? It was the matrix associated with T with respect to any basis. So just I have used that value, and this will imply lambda IV minus T of V is equal to 0. Now this is a key step over here. I have replaced this matrix by what? Now a linear transformation, and this vector x is replaced by what? a vector small v, but remember this small v is from the vector space V and this x was from R raised to n. So how is this V obtained actually? Okay, so since we have replaced matrix with a linear transformation, so naturally this vector has to shift from R raised to n to the vector space, because we know T is a map from what, V to V. So therefore we should have a element of V over here. So how we have obtained it? Just an example. Suppose I will take a case of R3. Suppose our vector is 1 2 3, then what I have done is, and suppose my basis has some vectors, let me say you can take any, but I will go for standard 1 0 0 0 1 0 and 0 0 1. Okay, suppose this is a basis of R3, then what I have done, simply multiply first vector by 1 1 0 0, second vector by 2 0 1 0, and third vector by what, 0 0 1. So that is going to give you the element of the vector space. In this case you get the same vector, that is 1 2 3, but depending upon the basis it may change. Okay, I hope you are getting it. Suppose we take some other basis of R raised to 3, then you can easily see that you will not get the same vector, the vector may be different. Okay, and that is this vector. Okay, now since we got this, now from here it is easy. So this will imply that T of V is equal to, now this IV will be what, it will be just V, because I is the identity map. And if you want we can do this in the previous step only, Ix च्या ऐवजी directly आपण इथे x लिहू शकतो, because I is the identity map and over here we will have V only, and therefore T of V will be equal to what, lambda V, and this will imply that this lambda is a eigenvalue of T and the corresponding eigenvector is V. Let us go with the proof. So therefore this will happen, and therefore this will happen. If you want just a change, since I is identity map x, since it is identity matrix, Ix will be x, and over here I will directly write it, just avoiding the complications. So V, and you can directly say TV is equal to lambda V, no need of this step. Yeah, and that is what we wanted to prove, and that's about this.